आइए हम सुने विज्ञान की अनकही कहानियाँ। आइए हम सुने विज्ञान की अनसुनी कहानियाँ। एक नई दुनिया की आवाज़ आपकी आवाज़, विज्ञान की आवाज़, की आवाज़।
We bring you a podcast series on STEM popularization, science, technology, engineering, mathematics and medicine, supported and catalyzed by the National Council for Science and Technology Communication, Government of India. This program is designed and devised by Dr. R. Sridhar and assisted by Ashish Tiwari, produced by Media for Community Foundation. Creative content and technical support is given by Purvasha Banerjee and Shushanto Das.
एक नई दुनिया की आवाज़ आपकी आवाज़, विज्ञान की आवाज़, की आवाज़, की आवाज़।
In this episode of the podcast series, we are immensely happy to receive a conversation from Professor Supriya. He will now be introducing himself and will be sharing his academic journey with us.
I am Supriya, currently a professor of physics in the Department of Physical Sciences at Bose Institute. I did my PhD at a Variable Energy Cyclotron Center in Kolkata only, but my work in my PhD during my PhD was an experiment that was done at the Brookhaven National Laboratory in the New York. The name of the experiment was solenoidal tracker at RHIC. RHIC means the Relativistic Avion Collider. I performed my PhD work there, and during my PhD, my involvement was building and commissioning of a detector that was named as photon multiplicity detector. The same detector that was used in the STAR experiment was again rebuilt in a different form in the ALICE experiment, that is a Large Hadron Collider experiment that is held in the Large Hadron Collider at CERN. After my PhD, I moved to the German laboratory GSI. It's in German name, that is Gesellschaft für Schwererdensforschung, that is Heavy Ion Research Society in German. There I worked for an experiment that is named as compressed baryonic matter. This compressed baryonic matter experiment is actually a proposed experiment that will be coming up in an accelerator that India is building partly. That means India is a founder member of the experimental facility, the accelerator facility for antiproton and ion research at Darmstadt. So in that facility, this CBM experiment will be performed. So during my postdoc days, I worked for that experiment. In particular, I worked for ring imaging Cherenkov detector that will be used for detecting the electron and positrons. After that, I came back. I joined Saha Institute of Nuclear Physics for 1 year. There I worked for the muon spectrometer at ALICE. And then I joined Bose Institute, and since then I am in the physics department. I started the experimental high energy physics activities here. In 2012, we also joined ALICE. Before that, that association was not there. And I also partly worked for cosmic ray experiments, which we have some detector array at our Darjeeling campus, Bose Institute Darjeeling campus. So this is all my activity at Bose Institute, and I'm also part of CBM now, both ALICE and CBM.
Now, Professor Dash will be sharing with us his area of research in a nutshell.
So overall, my area of research is the study of matter at extreme conditions. By extreme conditions, I mean extreme temperature and extreme density. And these two scenarios actually corresponds to two different physical scenarios. Extreme temperature is the scenario when the universe was created, there was no matter, there was only thermal energy. So at extreme temperature, the matter existed in a form of quark and gluons, a soup of quarks and gluons. And that is one area of research. And the other area is extreme density. Extreme density is the density that can be found in the core of neutron stars, that is an astrophysical objects. So that is another part of our research. But in both cases, the matter exists in the form of a soup of quarks and gluons. That is formally known as quark-gluon plasma. In one case, it is created by extreme temperature. In other case, it is created by extreme density.
Professor Supriya Das will be explaining his area of studies in details.
Actually, in Bose Institute, we work in a group. We have three experimental physicists in this area of research and one theoretician who is also working partly in the theory of this phenomena, what I told you, that this matter at extreme temperature. And myself and two other physicists are working both in CBM and ALICE. In ALICE experiment, our main goal is to study the jet phenomena. That is, there are many ways to probe this kind of matter, how this matter is characterized, how does this matter look like, what are the properties of that. One particular probe is the jet. Jet are when these nucleons or nuclei, they collide. Actually, what collides are the quarks and gluons inside them. So from those, and they are called partons. So when these high energy partons collide and they go back in other ways, then they start producing hadrons, other particles. So that phenomena is called jet. And now, depending on the density of the fireball that is produced in this collision, the jets are either they remain same, or they are sometimes quenched. Their energy is absorbed by this thing, by this material, by this medium. And probing that, we can tell about the properties of the matter. And in CBM, our activities currently, we have started doing the correlation fluctuation analysis at CBM using the hadrons. CBM experiment is not there, but we are doing the feasibility studies using Monte Carlo simulations and event generators like that. And using those kind of observables, what we can tell is that if we study the phase diagram, that is the diagram between the density and the temperature, there are two different phases. One is the confined phase of the normal nuclear matter, we see neutrons, protons. One is the deconfined phase of quarks and gluons, when the quarks and gluons from inside the hadrons or nucleons, they come out. And in between these, there is a phase boundary. So these two phases are separated by a boundary. Now, it is seen that the boundary ends at some point, and where this boundary ends is called a critical point. Now, whether there is a critical point or where the critical point is can be achieved by studying this correlation fluctuation analysis. So this is what we are doing now.
Professor Das now speaks on the collaborations.
If I can say, there are two levels of collaboration. First of all, we are part of an India-based collaboration where many universities and institutes are our collaborator. In Kolkata, we have Saha Institute of Nuclear Physics, VCC, they are our collaborator. And outside the state, we have Punjab University, IIT Bombay, IIT Madras, Guwahati University, Delhi University, they are all our collaborators. And then if I go abroad, then there are lots of countries who are collaborating in both the CBM and ALICE experiments. So this is two-level collaboration, I can say. A few years back, India was in the observer state in CERN. By observer means CERN is established by the member states. So they are the core group of CERN. They decide the policies and etc. And then there is another level that is called associated member, who are associated little less than the member state. They have their say in the council, but they are not members. And then farther away, there are observer states. So few years back, India was an observer state at CERN, but now India is associated member of CERN. So that I can tell that the status of India has got lifted at CERN. And in FAIR, that in Germany, as I said, India is a founding member of this whole accelerator complex, and India is associated from the very beginning of this project. So, and there are only 9 countries who are associated with this. So, you can say that India is globally ranked as one of the forerunners in this, at least in this area of research.
This is a great achievement for Bose Institute and our country as well. Professor Dash now explains some of the scientific technical terms and also shares a few information regarding the application of this research work.
First of all, this area of research, as I said, that we are probing and studying the nature of matter at extreme conditions. So, these extreme conditions, I told you that we are creating a Big Bang like situation in the laboratory. Like Big Bang created the universe. The universe started from Big Bang. So, to create that kind of situation in laboratory, there is only one way. This way is to accelerate heavy ions. Heavy by means of heavy, I can say oxygen, copper, carbon, gold, lead, this kind of heavier elements in the periodic table. If we accelerate them in relativistic energy and collide them together, the energy that is available as kinetic energy to the nuclei, they are converted into thermal energy, and that thermal energy creates the situation like a Big Bang in the laboratory. So, from that comes the names. ALICE is a large ion collider experiment. So, as I said, it is a large ion collider experiment. CBM is, I said that in the other extreme of the phase diagram, we have this core of the neutron star, where the density is very large, very large. It is the matter is at 5 to 10 times the normal nuclear matter density, where normal nuclear matter cannot exist. You can have quark, gluon, plasma. So, to achieve that, we have to have a compressed matter. So, that is why it is called a compressed baryonic matter. Why baryonic? Baryons are those particles that are either the nucleons or the mesons. Baryons are baryons, that is the neutrons and protons, and mesons are mesons. Those are pi mesons, k mesons, those are mesons. Mesons are constituted by 2 quarks or a quark antiquark pair, and baryons are constituted by 3 quarks. You can have quark and antiquark there. We collide with the nucleus. So, nucleus has protons and neutrons. So, when these protons and neutrons are collided, then you have only baryons. So, that is why it is called compressed baryonic matter. Now, the question is how humanity is being kind of helped by this benefited by this kind of thing. First of all, I must submit that this branch of research by research has nothing to do directly to the humanity. This is really a research of pure knowledge. But to do this kind of research, we have to have this technology which is very advanced. So, and achieving this technology gives us the edge to create new technologies. Like when this kind of accelerators at CERN or at FAIR operates, we need a very high level of vacuum, a very high level of cryogenics to cool the magnets, because these are superconducting magnets. So, all these technologies finally come back to the market in different forms. So, finding a direct contact to humanity is difficult, but I can give you 2 examples. One example is, I think by now everybody knows that the WWW was invented at CERN. So, the story goes like there were 2 people working there with one computer. I mean 2 computers back to back sitting on the same desk, this way, that way, and they had to exchange some information. So, internet was already available. Internet was first created in the US defense network, and then it was available in the 1990s. But what was not available is the web page that we see now. So, this Tim Berners-Lee, a British scientist, he was working and he had to exchange information with his other colleague who was sitting next to him on the other side. So, that was the idea came to his mind that if I can create a page that can be seen by the other person, I do not have to go and show him the results. So, that was the birth of WWW, and after that we now cannot probably survive without the WWW. This is one thing. And the second thing is this touch screen. We now have touch screens everywhere, especially in our mobile phones. The first instance of touch screen was the control room of CERN, where in this control room they control the accelerators. That was the first time the touch screen, capacitive touch screen was installed in CERN control room. So that technology also came to our humanity. Now, if I move to FAIR, FAIR is a multi-purpose facility. It is called Facility for Ion, Antiproton and Ion Research. There are different type of physics research. There is a fundamental difference between the AHC or CERN and FAIR. CERN is mostly for high energy physics research. But in FAIR, we have research in nuclear physics, research in high energy physics, research in plasma physics, and research in biophysics. Now, if I set aside the nuclear and high energy physics, which is mostly research for pure knowledge, we have this plasma physics and biophysics research. The plasma physics research is very much applied research, where one particular goal is to do the research for space technologies. The radiation from space that can be received from the to the space walkers, people going to the space station. That is a matter of research there. And in the biophysics, particular research is to do the research for the therapy, the therapeutic use of the particle beams for cancer treatment, especially for the brain and internal organs like lung and other places. So that is definitely going to benefit the human being.
We are immensely thankful to Professor Supriya Das for sharing a piece of his journey with us. Thank you so much.